Okay. Hello, everyone. Thank you for joining today's seminar. I hope you can all hear me okay. My name is David Rodriguez. I'm a systems engineer here at eSpace, and I'm particularly excited about introducing our speaker for this month. She's a good friend of mine and one of the brightest minds I know, Dr. Shreya Santra, assistant professor in the Department of Aerospace Engineering at Tohoku University in Japan, where she obtained her PhD on communication-based path planning for teams of planetary surface rovers in 2021 in collaboration with DLR's Institute of Communication and Navigation. Apart from her PhD, Shreya did her bachelor's degree in electrical electronics engineering in India, holds a master in space studies from the International Space University, where we met in France, and a second master's in space and engineering systems from Skoltech in Russia. So it doesn't get any more international than that. These days, she continues to work on various projects related to the optimization of space missions and has vast experience working with international teams to develop and design space systems. She's an active member of the Space Generation Advisory Council and has been recognized for her contributions towards the STEM, outreach, and SGAC activities. She also holds additional responsibility as the Director of Space Technology for Space Nova, a space education company, and Director of Technology and Outreach for Spaceport, and I'm going to mess this up, Sarabhai, I don't know how to pronounce that, sorry. Sarabhai, India's first space policy think tank. So before we start, as always, please keep your mics muted and cameras off. This video is being recorded and it will be uploaded to our YouTube channel afterwards. There will be plenty of time at the end for questions. So if you have any, please don't hesitate to write them in the chat. And I'll read them to Shreya at the very end. So that being said, thank you everyone for being here. And thank you, Shreya, for accepting to speak to us today. The floor is all yours.
Thank you, David. Thank you everyone for joining in today. And thank you, EPFL Space Center, for inviting me to give this talk for this month. So as David introduced, I'll just give a brief summary of about myself, and the agenda for today's talk is as follows. I will first introduce myself, and then I will introduce what is actually space robotics and the different applications of space robotics, and then I'll talk about the research at my lab here in Tohoku University in the field of space robotics, and discuss my own research that I did for my PhD and continuing to do. And also then I'll conclude with some closing remarks. So as David mentioned, I studied in India. I did an undergraduation in electrical and electronics engineering, and then I moved to Strasbourg in France for my master's in space studies at the International Space University. And that's where I met many bright minds who wanted to work in the space sector or study space. So that's what motivated me to keep going for in this sector and continue working in space related research. And so I decided to do a more technical master's in space systems and robotics at the Skolkovo Institute of Science and Technology in Moscow, and followed by a PhD in space robotics at the Department of Aerospace Engineering under the supervision of Dr. Kazuo Yoshida. And at this lab, I worked on the optimization of planetary surface exploration using multiple rovers. So currently I'm an assistant professor at the same lab, and also leading a space education and outreach team in India, which is called Space Nova, where I teach about extreme environment robotics. Okay. So coming to introduction of space robotics. So in the space community, any spacecraft that is capable of facilitating manipulation or assembly or servicing functions in orbit or on the planetary surface are called space robotics. And the first space robots were actually the result of the space race or the Cold War era between the superpowers, the USSR and USA. And such as like Apollo landings, which were in the 1970s. They had this moon buggy, and then the Luna Code 1 and Luna Code 2, which were the first rovers on another celestial surface and traveled several kilometers. Also, Viking 1 and 2 landers, they had robotic arms for soil sampling and in situ analysis of the Martian surface. And there were various robotic arms that were installed on the space shuttle or the space stations, one of them being the robotics demonstration, which was an autonomous robotic arm demonstration on board the STS Columbia by DLR Germany. So you can see here the different kind of robots or rovers that were launched back in the 1970s and in the 1990s, which was a sojourner on the Martian surface. So this is how the space robotics rose, and people realized, the space community realized, that these robots can send valuable data back to Earth from these extreme environment conditions. So robots actually have multiple applications on Earth, like in the factories or in the nuclear power plants, in the bottom of the seas, disaster sites and war sites, and also in the automobile industry. But what are the applications of robot in space? So there are various applications, but coming to the reasons why do we need space robots in the first place? We can have astronauts to do the work, but why do we need to have space robots? So the reason being, the primary reason is that space is a harsh environment. We all know it has extreme conditions of radiation, temperature, pressure, micrometeorites, also microgravity conditions, vacuum. And these areas are not actually accessible to humans or possible to work for humans. And that's why deploying robots are less risky and cheaper than launching humans in these unknown environments. And also the space environment and isolation and long duration space flights, these can cause mental breakdowns in humans, but in robots, these are not a problem. So that's where robots come to the rescue. And the different applications where robots can be used in space are scientific and commercial exploration, like we know the Perseverance rover or the Curiosity rover, as well as the rovers that will be launched later in the next few years, like the iSpace company is launching some landers and rovers. So for scientific and commercial exploration, for survey of planetary surface, so we want to find like different minerals on the asteroid, or some kind of water ice, or helium-3 on the surface of moon. And that's where robots can be very useful to survey these planetary surfaces, and also for assembly and construction on the planetary surfaces, as well as on orbit, like in space, and for service and maintenance, because, as I said, space is a harsh condition, and if humans have to work there, they have to put on many suits and gloves, and this actually limits the dexterity and the ability of humans to work in these conditions. So robots being used for servicing and maintenance are actually more effective than humans. And also for robotic landings, as we go to moon and to Mars and set up habitats, and we start launching and landing rockets from there, mostly these will be robotic, as we have seen, like we have seen the boosters of SpaceX rockets being like coming back to the shipyard, and that's actually a lot of robotic technology that's being used in the landings and launchings. So I think these are some of the applications for space robots. There are various other applications, but these are the main applications where robots can be used in space. So space robotic missions can be broadly classified into two categories. One is the orbital robotics, and these operate in microgravity conditions in the orbits. And these can do on-orbital servicing, removal of debris, asteroid capturing, mining, scientific data collection on board, and also work on board the space stations for experiment and assisting astronauts. And the other one is the planetary robots or surface robots that can operate on the surface of a planetary body. And the main tasks that these robots can perform are like coverage, landings and launch, surveying, in situ construction, maintenance, also scientific data collection and analysis on the surface of the planet. And these are mostly to expand the frontier of scientific knowledge and human presence in space. These are so coming to the next topic is, we know that there are these two different kind of robotic systems, but actually there are various challenges in the space robotics field that needs to be solved. Like space robotics is becoming a popular topic, but actually it's a very complicated research field. And there are challenges like the mobility and access in different terrains, localization and mapping in unknown environment, guidance, navigation, and control, and also autonomous capabilities of the robots. All of these are actually challenges that needs to be solved. Also reliability, remote operations, robot designs for different kind of environment, mass and power limitations, testing and qualifications, and many of these. So these are some of the challenges that needs to be tackled by the different researchers who are working in this field. And we here at the Space Robotics Lab, we have taken up some of these challenges and providing the state-of-the-art innovative solutions. So namely mobility in different terrains, localization and mapping, guidance and navigation, motion planning and control, inter-agent communication, autonomous capabilities, and autonomous capabilities. So some of these challenges we are like extensively working on and trying to solve with our systems, with our testings, and that we do in our lab, in our research group. So next I'll introduce my lab and what we do here. So the Space Robotics Lab is directed by Professor Kazuo Yoshida. He's very well known in both the space and robotics sector, and he is the chief technologist for the company eSpace, which was a spin-off from Team Hakuto, which participated in the Google Lunar X Prize, which ran from 2011 to 2018 and was one of the finalist teams. So he's leading the Space Robotics Lab since the late 1990s. And here in our lab, we conduct studies on locomotion, navigation, control strategies of various types of robots for applications in space environments. And we have many different collaborations with JAXA, NASA, ESA, DLR for these kind of researchers as well. So here you see the Google Lunar X Prize Hakuto rover, which was the engineering model for the Hakuto rover. It was supposed to fly to moon, but then the competition was cancelled, was called off without any winners. But now iSpace is actually taking this forward, and they are planning to launch landers and rovers in the next few years. So in our lab, we have different research groups, namely the Orbital team, the limbed robotics team, the Rover team, and the Terra Mechanics team. So I'll give a brief introduction of each of these teams and what are the topics that they are working on, what are the projects that they take up. So first is the Orbital team, and we all know that orbital debris, they pose a major threat currently. And if we do not take any urgent actions to mitigate this, like actively remove the debris as well as to mitigate the creation of debris, we will soon have no space for the future missions, especially in the low Earth orbit. And even the present missions will be in danger of collisions because of all the debris. So SRL is working on active object capturing using 2 robotic arms. So here you can see how it works. Like this is a pneumatic table where the robots are tested. It's like an air hockey table with the air coming from the bottom, and this gives an impression of the robots floating on the table. So kind of microgravity conditions. It's a 2D environment though. So, and here we are testing the capture using 2 arms. So this is one of the projects that's ongoing. And the other topics that that the Orbital team are working on is orbital control in microgravity, machine vision to estimate the pose of the debris, the capture mechanism, as I showed you here, the mobility mechanisms on minor bodies. We know that the minor bodies like the asteroid and the comets, they have very low gravity. So the mobility there is very different. So, you know, like hopping or kind of tumbling mechanisms without actually colliding or breaking with due to the impact. So these kind of mobility mechanisms are being studied and researched on. Also sample collection on asteroids and orbital robots for servicing. So here is a video from Hayabusa 1, sample collection technique that was designed at our lab. And here you can see how the spacecraft, it came down and then kind of like threw a projectile, and it created an impact which the soil went up into the tube, and that tube collected the sample and the sample was brought back. So this was the sample collection mechanism. And on the right is artist impression of how a servicing manipulator would be in space, and this is being worked on our lab, in our lab. The other team is the limbed robotics team, and here they are working on the dynamic analysis and design of limbed robots for challenging terrains, as well as for on board the International Space Station. And they developed the walking and climbing robots for challenging terrains like the moon, Mars. Like we know there are skylights or caves in moon where it is not accessible for wheeled rovers or like wheel rovers to go in. So that can be more accessible by climbing robots, robots which can climb on the ceilings or walls. So that's the kind of robots that are being designed and studied upon. And they design and study bio-inspired climbing mechanisms like insect-like climbing, as well as mammal-like climbing and human-like climbing patterns. And then they compare and design the robots here. And other than the design itself, a lot of study is also done on the perception, planning, and control techniques, including the reinforcement learning to train the robots for different kind of terrains and different areas, to explore different areas. The next team is the Terra Mechanics team. And this team is mostly working on safe locomotion methods that deals with the mutual problems between the soil and the wheels. For example, if the wheel rover is moving along a slope, there's a lot of slippage. And how do we enhance the driving performance and stability on these kind of terrains without actually letting the rover to slip or drift too much? And here you can see this, the robotic platform, which was the Eldorado. And this was being tested in the beach. And the other robotic platform here on the sandbed in our lab, that's the Moonraker being tested. So here we can like try to change the slope of the sandbed or the sandbox, and also try to change the compactness of the sand based on what kind of slippage or the cohesion and friction that we want on the soil. And that's how you can analyze and try to evaluate the driving performance through different and can be also done with different simulations. So these are the experiments, and there are simulations that are also conducted by our team members. Next is the Rover team. The Rover team is mostly working on the different software or algorithm development for locomotion, for path planning, also for perception and control. So we work on visual-based SLAM algorithms, also real-time map matching and image segmentation. We also do artificial intelligence and machine learning for rover localization and motion planning, as well as simulation to realistic hierarchical planning, myopic coverage path planning. Myopic coverage path planning means to have like a very myopic view that the rover can see, and just based on that, we try to plan the path of the rover. And this is mostly important when the platforms are small. For example, here you can see a small platform, which is Koguma rover in our lab, and also another smaller one here, Clover, which is also a micro rover. And these cannot see too high. So we try to do the path planning based on those, just the limited amount of field of view that the rover has. Communication-based path planning, which I will expand a little more, which was my PhD research, where these small micro rovers that can actually cover an area simultaneously, while also exchanging the information that they collect and exchanging the information that they see. And this helps in enhancing the coordination between the agents. And yes, as I said, development of multi-rover coordination and path planning algorithms. So in this team, we work both on single rovers and as well as multi-rover uh, exploration strategies. And here, the rover that you see, the big one, EX1, was actually developed by Dr. David Rodriguez and his team. And this was mostly developed for terra mechanics study, but now we also use it for our path planning and SLAM studies. So this is an example of image segmentation that we do for our rover localization and mapping. On the left is this is a these are fake rocks made up of styrofoam, and we are trying to detect different colored rocks by applying a masked RCNN model using a RGBD camera. So here we try to detect both small and big rocks that the rover is trying to navigate through, and it's used for obstacle avoidance. On the right is instance segmentation by fusion of RGBD camera and omnidirectional camera, as well as a 3D laser scanner. So here you can see there's a omnidirectional camera on the top, which can see the 360-degree field. And these are the rocks that are around the rover, and it's trying to map. And this is another rover. So it's trying to map this area, as well as trying to localize itself with respect to the other rovers. So this is an example of what we also do in our team. Next is multi-agent exploration strategies. So in the past few years, in the past few missions, it has been established that there's a lot of water ice and helium-3 deposits on the lunar surface. And with the most recent developments in the space sector, the moon is again back into focus as a major step for deep space exploration. And since single rovers are spatially limited and also slow in exploring, so that's where the multi-robot systems or multi-agent systems are becoming increasingly popular. And the near future missions, they plan to deploy multi-robot systems that are composed of several homogeneous or heterogeneous agents that will be able to cooperate to accomplish common goals such as mapping, surveillance, resource prospecting, servicing, etc. And these also incorporate a lot of cutting edge technology and demonstrate high-end autonomous performances. However, this precise coordination between these agents is a major challenge, and this can be solved. Like an approach to solve this is to involve inter-agent communication that will enable them to exchange the information. And the research in this field in inter-agent communication is actually progressing in really rapidly, as it helps in optimizing large-scale coverage strategies. And also, as we all know, like swarm robotics, they are more adaptable and robust, and also more scalable. So here is a illustration of how a communication mesh network on the moon would look. And why do we need communication? As I mentioned, it's of course it enhances the coordination, but also it emerges as a rational mode of interaction between the agents, and it is still not so easy for the agents to communicate with each other, because they are also in constant motion. And if we are using small rovers like the micro rovers, then we have the antennas really low, and that actually affects the communication quality. So on here on the left, you can see a communication mesh networking, how it would look on the surface of the moon. And here the green, the on the center is the lunar module or the lunar lander, and all around these are the rovers that are trying to communicate with the centralized lunar module. However, here the priority is not to communicate with each other, but rather with the centralized lunar module. And here on the right is the applying that mesh network on a genetic algorithm for path planning. And we try to cover an area with like 5 rovers. So you can see how it does cover, but there are multiple spaces that are left from covering, and that's because they are trying to communicate with the lander while they are covering, and that's why they are not able to cover all the area, all the spots in that area. So to understand the communication scenario on the lunar surface, I first modeled the radio signal propagation model and validated it with experiments. And these experiments, I did it at DLR in Munich, Oberpfaffenhofen. And there, although I modeled it for the lunar surface, but the base, the foundation is similar. So I could still test it and validate it on the Earth's surface with reliable devices, communication devices, and then trying to compare the trying to compare the data from the measurements of the experiments, and also what results I get from my model. And that's how I validated my model. And after that, I applied the model on my multi-agent path planner, which is a genetic algorithm with communication constraints, this time with 3 rovers. And it was seen that there were almost no disconnections as the rovers moved in configurations such that each of the rovers can maintain at least one link. And that link doesn't have to be with the lunar module. It can be with any of the agents. It can be with the rover, or it can be with the lunar lander. So, and that kind of enhanced the trajectory, and also the number of goal points were actually covered. All of the goal points were covered, but the goal points were not visited twice by the rovers. And here is a small simulation. So they start from certain configuration and they start moving, and the links that you see is the signal strength or the signal quality. So this is the main communication constraint, that the signal quality should be at least 60 dB, and that's how they can communicate with any information exchange. So on the right is the trajectory that's followed by the rover, and on the left is the instantaneous link that's being formed at each point. And so if the communication constraint is there, they try to move in a way that there is multi-hop communication, or kind of relaying. So each of the rover, they act as relay for the other one, which is far away. And that kind of helps in coordinating the trajectory between the rovers. So the main takeaways from this communication-based path planner was that the communication constraint path planner solution actually generated coordinated trajectory for the rovers, and the total distance that was traveled is slightly higher as the rover actually chose the configuration with maximum link possibilities. So as I said, the path planners usually optimize it in terms of shortest path length or shortest time. But in this case, when I applied the communication constraint with the good signal strength, it increased the distance, but it was not a lot. And it also reduced the number of disconnections, and the goals were not revisited because the rovers already knew which of the goals have been visited already. And also it reduced the risk of losing the rovers and the information when the connectivity or the link was maintained. So this was my research. I cannot show the paper, the numbers, because I have to publish it still. There are some things that need to be published, but basically these were the outcomes. And yes, I have other papers on the validation and the model itself, which can be found on my ResearchGate profile. And yeah, I would like to conclude with the future of space robots. So many robotic missions are being planned in the near decades, and like the Titan mission, which is like a flying robot, the Dragonfly mission, which is a flying robot on Titan, and the Martian moon exploration mission, which is by a consortium of JAXA and also CNES and DLR. And this includes Orbiter as well as a kind of hybrid rover on the Phobos. And these are very interesting technologies that are being deployed on these robotic systems. So space robots is actually the frontier of exploration, and there are a lot of possibilities that can be uncovered by the space robotics technology, and it's a rapidly growing field. Of course, there are many challenges to address, but it's also a very exciting field. So testing them, developing them, that's a very exciting thing to do. And the Artemis mission will actually incorporate multiple robotic systems and expeditions to the moon. It includes crewed mission, but also many robotic expeditions that will actually, prepare the place, and also as a precursor before humans land there on the moon. And it's an interesting potential both for academia as well as commercial new space companies. So definitely look out for all the opportunities in this field. And with that, I would like to conclude, and I hope you enjoyed my talk. Now I'm open to questions.
Thank you, Shreya. That was a wonderful talk. I don't know if anyone here in the room has any questions. Go ahead.
So maybe I can ask it directly here.
Yeah, sure.
So thank you for the talk. My question was about the debris capture mechanism.
Yeah.
You showed the video when it's on a 2D environment. When you imagine it going into a 3D environment, how many arms will it have in total, and will it have force feedback for knowing the force that is applied on the captured object?
Yes, it already has the force feedback, the tactile sensors to understand the force that's on the captured object. And for 3D environment as well, it's the two-armed capture system. So in the simulations, it's 3D and it's still two-armed capture system. So this is the system. It's only being tested on the 2D just to have the floating, floating impression, so that while it's moving, it can be captured.
Again, does the robot need to know the center of mass of the object before it starts trying to capture it?
So yes, it tries to do the pose estimation of the debris, and also from the debris databases, it can calculate what's the mass and the other properties of that debris, and using machine vision and the mass CNN as well here. So it uses that and also does the pose estimation, orientation, and center of mass of the object to capture.
Okay, thank you.
And we have a couple questions in the chat. I'm gonna read to you. Are these examples shown carried out in the Earth environment, pressure, temperature, like on Earth? And if so, how can you test the impact of space, of the space environment? With these examples, I think he meant, the images that you showed, Moonraker and the like.
Yeah, so these examples are actually done on Earth, with not with the pressure and radiation and temperature conditions, because each of the teams, they are working on some certain problem statement, and we are trying to solve that specific problem statement. But when we are building the whole spacecraft for space, for example, right now we are also working with JAXA and Toyota to develop the big lunar truck. So for that, we have a huge sandbox, and it is controlled. So that's how we kind of try to create a controlled environment for specific projects, but not for all.
Great, and there's another question about what's the maximum number of agents that can be deployed using your multi-agent algorithms?
Yeah. So from the simulation, so I haven't yet done it in hardware or the real experiments for this communication-based path planning. It's mostly simulations, and I tried it for 3, 5, and 9 rovers, and the best results were for 5 rovers. So of course we can use as many rovers, but it's all about optimization for a specific area. And in this case, it was 2 kilometers by 2 kilometers area, and 5 rovers with because I had to trade off between the distance that's covered by the rover, as well as the how many times there are disconnections between the rovers. So that's 5. To answer your question, 5 is the most optimized number of rovers or agents.
Awesome. I don't see any more questions in the chat. I don't know if here in the room anyone has any other questions. If no, I have a couple, just out of curiosity. So for your algorithms, the communication-based planning, is there So you initially said that the communication is between the agents and the lander always?
Initially, I did the mesh networking with the centralized lander, but in this case, it can be with landers as well as it can be with rovers. So it's not a constraint here. The main constraint is the received signal strength between the agents.
Got it. Okay. And how are you going to go about testing or validating these algorithms? In terms of, you know what I mean? Like that's a big part that we always suffer from in space robotics, which is moving from what works very nicely on our computers to field tests.
So I want to be more realistic about it, and when I test this, I don't want to just have the communication as a constraint, but I also want to combine the visual and inertial SLAM, so that the rover, in this case, yes, the rover is autonomous. In my simulation, I have assumed it's autonomous, but when I do the experiment, that autonomy will also come from the rover's capability to understand its environment. And so if I'm using the SLAM algorithms as well, including radio localization, so that's how I want to optimize it. And like this, my model can be easily applied on the already existing, in addition to the already existing SLAM and radio localization constraints, and then using that on the path planner, it will actually optimize the whole trajectory and the coverage performance.
Right. There's a new question in the chat. What are the environmental factors that will play prominently in affecting the communication between agents?
Yeah, that's actually a very good question. So the main environmental factors are the surface properties, like on the moon, the permittivity, the conductivity of the soil itself, the regolith, that affects the signal attenuation and how the signal is propagated between the agents. In addition, also, if you are taking the environment, yes, there's no atmosphere, so there's less of free space loss. But at the same time, we are trying to use low or short-heighted antennas, which are for micro rovers, and the shorter the antenna is, the more the signal will be reflected by the surface. So, and the lunar surface is actually, it causes a lot of reflection. And also, if there are craters and rocks, it includes like there are knife edge diffractions of the signals and bending of the signals, and that again affects the communication quality. So all of this is actually the main modeling, where I try to analyze the terrain between the one point to another between the agents, and then based on the terrain and based on the the surface properties of that site, the model is done, and that's how the signal strength is predicted. I hope that answers.
So yeah, I don't see any more questions. I don't have any more questions myself. If there are none, then we can probably wrap it up here. Just by saying thank you to you, Shreya. Oh, there's one more. Just like we still have time. So, are there any open source simulations for space robotics?
Yes, so most of these simulations are done open source on Coppelia Sim, which is for education purposes. It's free software, Coppelia Sim, and also we work a lot on Gazebo and the simulator called Gazebo, where which is also open source. Of course, there are other simulation softwares, but it's mostly Gazebo and Coppelia Sim for us. We are also looking into Unity 3D for reinforcement learning, but it's a little steep learning. So yeah, we are trying to explore that as well.
Great. So yeah, with that, I'll wrap it up. As I was saying, thank you, Shreya, for making the time to talk to us, and thank you everyone for joining. If if you're interested, I posted in the chat the link to our YouTube channel where we have all the previous seminars, and this one will be there pretty soon. So yeah, thank you everyone, and I'll see you again next month. See ya.
Thank you.